Okay, hybridization. I think we're ready to talk about SP and F9. Let's see where we're at on the outline. So we did ethylene last time. Pi bond. One of the main consequences of the pi bond is that it can't rotate. Yeah? Sigma bonds can rotate head to head. We showed that, right? We'll do lots of rotations. This bond can rotate because it's a sigma bond. The things attached to it rotate, yeah? All right. Pi bond can't rotate. All right. For example, these two things are fixed side by side. You cannot rotate this because you got pi bond here, side-to-side overlap between the two carbons. All right. Try to rotate it, you're going to break the pi bond. You can't do that. The molecule's not going to do that. Now you can break pi bonds. I can pull out my lighter and it's going to break all the bonds. Turn them all into CO2. Yes, you can break it, but it requires energy. But this guy just hanging out on a Saturday afternoon, it ain't going to be rotating. Okay? Can't rotate. We'll talk more about that, consequence of that. SP hybridization. You got to have at least two carbons to have an alkyne. Let's look at this here. How many electron regions? These are the questions. How many electron regions around this carbon here? This structure, 2. Okay, that means we need 2 hybrids. Regions equals hybrids. We need 2 hybrids. Ground state has, we've had that drawn before, right? 2s, 2p, boom, boom, boom. We need to make 2. You're always going to make this one, that one, and one of these. So we're going to blend these 2. You blend those 2. If we put 2 in the blender, how many hybrids are we going to get? You put 2 in, you're going to get 2 out. Okay, what are we going to call these? Well, we blended an S and a P. We're going to call these just simply SP. This is 2 sp2 hybrid orbitals. We still have the 2 p orbitals left over. We did not do anything with them. They're there. A hybrid orbital set the geometry. The hybrid orbitals are used to make sigma bonds. Look at this carbon. What do we see? What type of bonds do we see? What type of bond to H? Sigma bond, using a hybrid. Sigma bond to H. What else do we see? It's actually making a sigma bond to carbon. Okay? We draw a carbon here. 2 hybrids, how are they best spread out? How are they going to spread out? If I tie 2 balloons together, how do they spread out? It'd be linear. Okay? 2 balloons would be like this to each other. If you tie them together in one, and they're like that, please show me. You're not going to do that. They're going to be linear. These 2 hybrid orbitals are linear. What do the hybrids look like? We'll compare relatively. I'm drawing them pretty much all the same. We'll have to make relative comparisons. Hybrids. Linear. This one is interacting with the H orbital, which is an S orbital, right? There's your H, 1 electron, 1 electron. Okay, I showed it as 2 arrows. Here I'm showing it as an arrow and an H. Making sigma bond, head-to-head overlap of what type of orbitals? This is an S and this is a what? An SP. Hybrid. You got another SP. It's interacting with what? Actually the other carbon. The other carbon is the exact same. And it has 2 sp hybrids. It's supposed to be the same. Okay, that one looks better. It's supposed to be the same. Magic going on right here. 1 electron interacting to make sigma bond. That's this here. Because here I'm focusing on this carbon. Making a sigma bond using its electron, and then the other electron I'm showing as a C coming from the other carbon. All right? 2 sigma bonds. What else is on this carbon?
2p.
2p orbitals. One of them is straight up in the board, the plane. Well, this one over here is the same exact. It's got 1 here. And guess what they're doing? They're interacting. Because there's one electron here and there's one electron here. And the two orbitals, the two electrons in those orbitals come together, interact to make a magical two-electron covalent bond. Well, this is side-to-side overlap of these two p orbitals. We call that a pi bond. What else is on this carbon? The other p orbital. It has two, right? I only drew one. The second p orbital. How is it in position to the first? As you learn in Gen Chem, your p orbitals are all orthogonal to each other, 90 degrees. Boom, boom. Okay, like this. Gen Chem, boom, boom. And then the third one is what? It's coming straight out at you, all 90 degrees to each other. Right? The other one here is coming straight out here. All right, how do I draw that? And half back. Okay, here's the board. It's like this. How do I draw this? It's difficult. It's easier to look at pictures, which have been more sort of have a better 3D. I'm going to draw it sort of like this. But guess what? These are interacting as well. Okay? One electron, one electron. Okay, you've got two p orbitals interacting like this, which I drew flat on the board, like that pi bond. But you also have two p orbitals interacting like this. And that's the second pi bond. All right? Picture in the handout is better than what I tried to draw here. Of course, this over here is to an H, magical. That carbon is the same exact thing. What do we have between these two carbons? How many bonds? 3. Sigma bond and 2 pi bonds. Total of 3 we call a triple bond. Okay? So what do we have up here? We have a pi bond to carbon, and all together, what is this? That's your triple bond. So, we can go back and look here. What do you see here? I see a sigma bond to H and a sigma bond to carbon. And then I also see 2 pi bonds to carbon. We've got to know what a triple bond is. On the other hand, a double bond was 1 sigma and only 1 pi. Right? Ethine has 2 pi bonds. There's 4 pi electrons. What's a pi? What are pi electrons? Pi electrons are electrons that are in p orbitals. Okay? How many electrons in p orbitals in this molecule? One, two, three, 4. Yep. Each pi bond has 2 electrons. Right? How many electrons in a bond? 2, right? Okay, let's go from there. Pi bond, p orbitals, pi electrons. Bond lengths, bond strengths. That would be in the table on functional groups. Yes, functional group white handout. There's some pictures, including what we just looked at here. Okay. A little bit better 3D view than what I drew kind of quickly. All right. Sigma bond. Now this is not 4 pi bonds, it's just above and below. So I'm indicating the above each with the sort of pi, right? We got another can you call that a pi interaction, but there's pi interaction above and below to make 1 pi bond. So you can look at those. Bond angle, of course, 180 degrees, linear. So the HCC bond angle would be 180 degrees, linear. Yeah? It should be all be here. Any questions about any of this? Should look a lot like Gen Chem, yeah? Yeah? Okay, orbitals. I drew an SP, we combined an S and a P and sort of showed it back lobe, okay? But we really didn't make any relative comparison. Relative comparison here, again, my crude drawings. 3 different types of hybrids we looked at. Main thing here is percent S character. This is 50% S, okay? 50% S, half S, FP. What's the percent S here? 33% S. And this here? 25% S. Okay? It's kind of like how much chocolate is in your mix. All right? If you had 50% chocolate, it's going to be more chocolatey than a mix that only had 25% chocolate. All right? More S character. What do you know about an S orbital compared to a P? S orbitals are shorter, right? In terms of length, I mean, an S orbital is like this, where a P orbital is like this, right? So which one goes that way further from the nucleus? Obviously the P orbital. P orbital is longer. S orbital is shorter and fatter. Okay? So the more S character, the hybrid's going to be shorter and fatter. But this gives you your bond lengths. Because a bond using an sp hybrid is going to be shorter than a bond using an sp3. All right? This also gives you your strength of your bonds. Because which is more stable? S or P? Stable meaning lower in energy. S is lower in energy. Yeah? When you graph ground state, S comes lower than P. Okay? So which of these 3 hybrids is most stable? The one with the most S character. And typically, if a bond using a more stable electron is going to be stronger. Bonds made with sp hybrids are going to be stronger than bonds made with sp2 or 3 hybrids. The electrons are more stable. They make stronger bonds. So a lot of this, in this table we're fixing to look at, comes from percent S character. And if you understand that, you're going to be well on your way there. Question?
Is that why single bonds are generally stronger than double bonds?
Single, no, a double bond stronger than a single. But I wonder, you might need to clarify your question and think about it and make sure that you're satisfied with my answer. Triple bond stronger than a double, yes. But the sigma of a double is not as strong as the sigma of a single, though, I believe. You got to dig into that question. But overall, a double is stronger than a single. Okay, the table here. Need to know these trends. Okay, ethane. Every carbon in ethane, both carbons are sp3 hybridized, right? Got to be able to recognize that. sp3 carbon. How many regions around this carbon? 4. 4 is going to be sp3 up until we have an exception. A huge exception. No exception here, though. And sp3, once you know that, and everything that comes with that. Okay? Well, for these sp3, H is not hybridized. It's just an S. It's just using an s orbital. Bond angles of sp3, 1 to 9.5. All these bond angles here. Length of the carbon-carbon bond, typically in angstroms, 1.54. Let's compare other lengths. Here, both carbons are sp2. How many regions around this carbon? 3. 3 is going to be sp2. What all that comes with. How you end up with the pi bond there. HCH bond angle would be 120, as well as the HCC bond angle. Length of the carbon-carbon bond, or the Interatomic distance between the carbons. Shorter. These are closer. The bonding is closer. Why? Everything comes from hybrids. This is sp3 bonding to sp3. This is sp2 bonding to sp2. We're just looking at the sigma bonds. Which bond would you expect to be shorter? A bond using these two orbitals or a bond using those two orbitals?
SP2.
Here. Because these orbitals are shorter than those orbitals because they have more s character. And that's why you have a shorter bond. Got to be careful. I reckon that's clear. They are talking. That's clear. Down here, this sigma bond comes from sp interacting with sp. Two shorter, even shorter orbitals interacting, making the interatomic distance even shorter. You don't really need to know the absolute number, just the trend. Although it would be good to know how long a typical covalent bond is. Typically, 1 to 2 angstroms is their average. Strength of the carbon-carbon bond. Gotta be careful. Are they talking about just the sigma bond or the entire bonding? I think they're talking about the entire bonding between the carbons. 90. Double bond stronger. Triple bonds even stronger. Yeah. But, okay, but is this double? It's 2 bonds. Is it double this? No.
So does that mean the sigma bond is weaker?
Is what?
Does that mean the sigma bond is weaker in the sp2 bond
Let's look at
than
it.
in the sp3?
Let's look at it. This is 2 bonds, but this is a sigma. But this is a sigma plus a what?
Pi.
Pi. Yes. Which sigma is stronger?
sp3.
No, this sigma is stronger because these orbitals are lower in energy. More S character, lower energy orbitals. This sigma is stronger. So for example, I don't know the number. It's stronger than that. This sigma may be 100 and, well, let's do it this, maybe 98. 98 for the sigma. And now I got to do some math. What's that, 76? For the weaker pi. Is a pi bond weaker than a sigma? Yes. Head-to-head overlap is best. Side-to-side is not as good. You might think it's better because it's more there. Problem is, they're kind of far apart. Pi bond tends to be weaker. So you see here, the sigma bond is stronger. Okay? But you do have the pi bond. And of course, overall, a double is stronger than a single. You got to know what's here. Now this, is that triple this? No, because it's not 3 sigmas. What is it? It's a sigma plus 2 pi's. This sigma is going to be stronger than that one, and stronger than that one. Again, maybe this sigma is 105. And then you add these two. Don't worry about the numbers, the trend there, okay? Sigma bond gets stronger. You don't know what they're talking about here. It looks like, are they talking about the sigma or the total? I wish they had used, been a little bit more clear right there. Length of the CH bond. Are all CH bonds the same? No. Why is this one shorter? Because this one comes from SPS, SP2S, SP3S. Which bond would you expect to be shorter?
SPS.
SPS. Because the SP is shorter than the other ones. And of course the S is constant with each of those bonds. The H is always just an S. Percent S character. Okay. Bond strength. Why is this bond stronger down here? Because the carbon is used in an sp hybrid. That bond is going to be stronger than this bond. Hopefully all that up there can be understood by percent S character, yeah? It can be. Make sure you understand it. Type of questions down here. Let's see how we did. Bonds A through C, which can rotate? A, B, and C, which of these can rotate? A and
B.
A and B, yes. Yes, A and B can rotate. Why can C not rotate? Why can C not rotate?
Because of the double bond.
Do what?
The double bond. The pi bond.
There's a pi bond here?
On either side.
On its two.
What type of bonding do we have? I mean, what type of bond is C? Can a sigma rotate? Right? Yes? Head to head? Yeah? Why do you say C can't rotate? Come in again?
Because it's in between those double bonds,
There's resonance.
I just can't hear you. I hear a ring.
because it's in between the double bonds? Or are we thinking about that?
I wonder why I asked that question at this point. Which could rotate. It's a very common question. We need to know. We need to know that. C is a little bit. C cannot rotate. There's two reasons. First off, it's in a ring, and you're not going to be able to rotate this ring. More importantly, though, you got p orbital, and you got some interlap there. There is pi bonding between those two carbons. Yeah, I agree. Okay. Each carbon has a p orbital. The orbitals are going to be interacting, and that's going to restrict rotation. All right. Question?
Does it have anything to do with resonance?
What I just described is basically getting into resonance conjugation. Okay. Does everybody agree that each of these carbons has a p orbital?
Yes.
Okay. They're adjacent. They're going to be interacting. The interaction is going to restrict rotation. Okay. We can talk more about it. Sometimes I ask you questions. We're not ready for the full answer, but I'm giving you a heads up. We need to be thinking about types of things. Which types of bonds can rotate? What is the hybridization of each atom in Prozac? That's the structure there. Yeah. What's the hybridization of each atom? Okay, let's look at this. What's the hybridization of this carbon right here?
SP3.
sp3. Yeah, 4 regions around it. Graphing. Okay, I'm big on graphing the hybridization. Books will do it at the very beginning when they describing it to you. And then they won't do it anymore. I don't know why. Graphing the hybridization is very useful. It helps keep you organized. It gives you a systematic way to do things. Okay. That carbon right there, yes, sp3. That comes from 4 regions. I know sp3 is 4 hybrids. What type of bonds do you see this carbon making? I see sigma bond to F, sigma bond to F, sigma bond to F, and sigma bond to carbon. Everybody agree? That right there? And that is the graphing of the hybridization. You can show energy here, you can clean it up. There's no p orbital. We used them all when we hybridized. All right? sp3 pretty straightforward. How about this nitrogen here? Can you graph its hybridization? A nitrogen there.
SP3.
sp3, how many regions around that nitrogen? 4. Okay. Just make sure you indicate what that is there. That nitrogen there. Let me do it up here. sp3 again. Which is boom, 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 boom. What type of bonds do you see that nitrogen making? Sigma bond to carbon, sigma bond to carbon, carbon, carbon. Sigma bond to H, And what else?
Just a lone pair.
Lone pair. Lone pair is sitting in one of the hybrids as a non-bonding lone pair. Okay? Okay, here we go. If we show that nitrogen, what's the geometry of the electrons around that nitrogen? No, sp3 is tetrahedral, right? Tetrahedral. How do you draw a tetrahedral? 2 in the plane, 1 forward, 1 back. Okay? That's not shown in a tetrahedral manner. That's not the true geometry. You got one of these is to an H, one of these is to a carbon, one of these is to a carbon, and then the lone pair is occupying the other region. Okay? That's what you have there. That's the geometry. And then you finish everything up. What's the bind angle between the H and C? 109.5. It's all there. Okay? Really, the only thing new is I'm just trying to make sure you understand that the lone pair is occupying one of the regions of the tetrahedral. Right? And that's a hybrid orbital. Of course, this is a hybrid orbital interacting with the hybrid of the carbon. This is a hybrid orbital with a backload that's interacting with nothing. It just contains 2 electrons, what we call a lone pair. But it's still in that region. Okay, what's the hybridization of each atom there? I'd like to do another nitrogen. Let's look at the syllabus sheet. Cipro, which is also on the DQ page. Cipro. What's the hybridization of this nitrogen? Does have a lone pair, right? You got to know where lone pairs are at. How many regions around that nitrogen? 4? 4. Hybridization? sp3? Okay. In this case, no.
sp2.
Yes, this nitrogen's sp2. Exception. Exception from anything you've seen even in Gen Chem. They're not going to tell you this in Gen Chem. That nitrogen is sp2. Since it's sp2, graph it as sp2. So sp2 would be what? How many hybrids? 3. What's left over?
P orbital.
1 p orbital. Okay? What type of bonds do you see this nitrogen making? Single is sigma. How many sigma bonds? 3. Sigma bond to carbon. And an important question here always is, what type of orbital is a lone pair in? How do you know? Because that's all that's left? Yes. What type of bonds do you see being made?
Sigma with carbon.
I see 3 sigma bonds to carbon, right? Sigma bond to carbon, sigma bond to carbon, sigma bond to carbon, using your 3 hybrids. Where must the lone pair be? Indeed. That's a p orbital. A lone pair in p orbital. Yes, has to be if you'd start with, if it's sp2, and I've told you that. But this is why it's sp2. And here's where the exception comes. Anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital. Is there a p orbital on the adjacent atom here? What's its hybridization? sp3. There's 2 H's there. sp3. No p orbital. How about here, though?
sp2.
That carbon is sp2 with a p orbital. In fact, every atom of the ring has a p orbital, which is why it's aromatic. Definition of aromatic on the functional group page. Okay. Anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital. This lone pair is in a p orbital. Okay? Those orbitals should be the same size, or basically. Why? Because lone pairs, they're like They don't have anything to do. They're lonely. They want to interact with something. Okay? And if we, in this situation, they get to interact with the neighbor there, the neighboring p orbital. And you get some pi bonding. And that is a very stabilizing thing for the molecule. That stabilization drives it away from sp3. Why would we say sp3? Because 4 regions is best spread out tetrahedral. But in this case, we have something that overrides that. Here, having the lone pair interact with the neighboring p orbital is an overriding factor, and instead the molecule adopts an sp2 configuration there at that nitrogen. And that's what we have. And actually, because it's sp2, the bond angles around there are 120, not 109.5. And so everything that comes with that. There we go. Question?
That's a little bit like what we just went over. So that bond couldn't rotate because of that p orbital.
Good, good. What you have to do moving forward is you have to recognize there's some pi bonding here, even though the structure doesn't show it. Because a lot of times the structure we show is, we draw, does not give us all the details. We've got to know more details there. Yes, there's probably limited rotation between the nitrogen and this carbon. Very good. And also, like I said, bond angles are going to be there. There are many consequences to this being sp2. Okay. On the other hand, how about this nitrogen? There's a lone pair. What's its hybridization?
It's sp3.
It's sp3. And the lone pair is in what type of orbital? sp3, because an sp3 hybridized atom only has sp3 orbitals. There's no p orbital there at all. There's no reason for that one to be sp2. There's no p orbital next door. Yes, we call this conjugation or resonance. But I won't start calling it that until a little bit later. But what we're doing is we're setting the foundation for resonance. I'm telling you the truth. Some books will actually, in chapter, I've seen it before, some books in chapter 1, this is sp3, and then all of a sudden over in chapter 12, they start calling it sp2. Because they didn't want to lie to you in chapter 1. Or no, they did want to lie to you. They lied to you in chapter 1, because they didn't think you were ready for it. All right? To me, this just leads to confusion. All right, graph the hybridization of this oxygen up here. What is the hybridization? There's 2 lone pairs. Hybridization? Hybridization?
sp2.
sp2, yes. That means we have boom, 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 and boom. What type of bonds do you see that oxygen making? Sigma bond to carbon, and what else?
Pi bond.
Pi bond to carbon. Now let's see a double bond, and a double bond consists of a sigma and a pi. Right? Where are the lone pairs?
In the sp2.
The lone pairs are in hybrids. So, are these pi electrons there? Are those lone pairs considered pi electrons? What's a pi electron?
Has to be the p orbital.
Pi electrons are those that are in p orbitals. Are those electrons in p orbitals? No, they're in hybrids. All right? Now remember where p orbitals are at. I recommend graphing. It helps keep you organized, and it gives you your answer. If you want the answer easily, I would graph it. If you don't want the answer easily, then... Okay? How about the fluorine? Anything you can say about it? First off, 3 lone pairs, right?
What about will that act the same as nitrogen? Will it have?
Yes, what I described for nitrogen applies to anything.
sp2.
Anytime a lone pair is next to a p orbital. Didn't say anytime a nitrogen lone pair was next to a p orbital. It said any lone pair. Is lone pair next to a p orbital? Yes. Only one of them. One of these is going to be in a p orbital. That fluorine is sp2. And so we have boom, 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 boom. How many what type of bonds do you see?
Sigma bond with carbon.
Sigma bond with carbon, then the rest are lone pairs. But guess what? One of them is in a p orbital because there's a p orbital next door. And we have some pi bonding there. The other two are in hybrids. Please don't try to draw every single thing. Some things you can just look at and see. You try to draw it, then you're not going to be able to see what I'm doing. There's that. sp2 trigonal planar. There's your trigonal planar. That's to a carbon. But this is a lone pair. This is a lone pair. There's your trigonal planar for the sp2. But then the other lone pair is in the p orbital. Okay? Because you got... But you still have that trigonal planar of the bond lone pair, lone pair. Okay? The electron in the hybrid. There's plenty in the my workbook for doing hybridization. Should be also in your textbook. Where's the outline? Green, yeah? Let's look at a couple other things. We did 3 first. Atoms other than carbon, we did. Let's go back to carbon a little bit and introduce a couple of ions. Carbon with H. What about this here? First off, charge of that carbon.
Positive.
Yes, it's positive. Got to be able to charge. We'll see lots of positive carbons. This is called it's a carbon that's a cation. It's called a carbocation for short. Carbocation. Fairly common. What's the hybridization of this carbon? Bond angles, geometry, all that stuff. Hybridization? Hybridization?
sp2.
2? Someone would say sp3?
Yeah.
No, 3 regions. 3 regions is sp2. Okay, boom, boom, boom. P orbital here. Left over, not hybridized. What type of bonds do you see there?
3 sigmas.
Sigma bond to H, sigma bond to H, sigma bond to H. What's here?
1 electron.
No, if it was 1 electron, it wouldn't be positive. Why is it positive? How many electrons does the carbon own?
3.
Owns 3. Well, there are the 3 there. The arrows are the electrons that the carbon owns.
So there's nothing in the pH?
Correct. Empty p orbital. It does not have an octet. How many electrons around this carbon? 2, 4, 6. It's missing 2 from an octet. An empty p orbital is what we say. Do you think this would like electrons? We had this species, this molecule. Do you think it would like electrons?
Yes.
It would like electrons because it would like to achieve a filled octet. Something that likes electrons is going to be called an electrophile. Somebody who likes wine is called a winophile. Molecule that likes electrons is called an electrophile. Electrophile will be a very common term as we go along. Make sense? Also electrophilic. This molecule is electrophilic. What does that mean? Well, we'll add to that, but that's, okay. What's the HCH bond angle? I drew it as 90 degrees, is it? No, what is it really?
120.
Right, and geometry? It's like that, 120, 120, 120. Trigonal planar, all that's in the plane, nothing forward or back. Now the empty p orbital is perpendicular to that. Okay? Half coming out, half going back. Right? Board here, and then your p orbital this way, right? If you want to believe there's a p orbital there or not. But we call it empty p orbital. It's all there. This thing over here, really need to see what type of questions come up. Okay? What I can't do and what I am not going to do, because it's not the best way to do it in my opinion, is for me to tell you the little nuances that all go with that. It'll take us 2 lectures and then we'll be so far behind that we'll have to just rush. I'd rather respond to your questions. Then we could focus, particularly you, that will also help the discussion. So see what type of questions you have about that exception over there. Internal lone pairs next to a p orbital. Okay, start working with that, yes.
In the case of the fluorine in the Cipro, it had 3 lone pairs adjacent to 1 pi bond. Had there been another pi bond, so it was adjacent to 2 pi bonds, could 2 of those lone pairs interact with?
Do you want to call this instead of p orbital instead of a pi bond?
Oh yes.
Okay, so it's next to 1 p orbital. You're asking if there were 2 p orbitals over here?
Yes.
Yes, it could. You could have another one interacting. One lone pair interacting like this, then the other lone pair could be like this.
So what would be the hybridization on that then? Would it be just SP?
That would be SP. Yes. What you described is theoretically possible, but we will rarely ever see that. But it is possible. Hopefully it makes sense that it's possible. I mean, yes. If one lone pair gets to interact, why would the second one not? It's possible. Very rare though. Yes. Okay, and it doesn't have to be nitrogen, fluorine, oxygen, for example. Over here, you've got some conjugation there. Let's look here. Another one. Oh yeah, I wanted to, how about this carbon? Let's have 3 H's, but instead of nothing, let's put a lone pair. What's the charge of this carbon? How many does it own?
5.
Owns 5. This is a negative. It's a carbon that's an anion. What do you want to call this one? Carbanion. When carbon's a anion, we call it a carbanion. Less common than cations. We'll see lots of cations. Carbon prefers to be cation rather than anion a little bit. But it can be anion also. Hybridization here.
SP3.
SP3. Good old SP3. What type of bonds do you see? Sigma bond to, what do we got? H. Sigma bond to H. Those are arrows, sigma bond to H. And what else is there? Lone pair. All in a tetrahedral arrangement. By the way, I only deal with electron geometries. I don't talk about molecular geometry. I don't see how you can ignore electrons. Okay. For example, water. Water to me is tetrahedral. The oxygen is tetrahedral. In Gen Chem, you probably called it bent or something. That's because you're ignoring the lone pairs. Let's ignore the lone pairs and talk about geometry. I'm not going to do that. I will never ignore the lone pairs. The geometry of the oxygen to me is tetrahedral. Yes, the bond angle is 109.5, but, and yes, it's bent, because if you know what a tetrahedral is, you can see that the HCH bond angle is bent. Okay. carbanions and carbocations. Here we go. Okay, we need to get through up to this point, at least today. Tad bit behind. I need to start really looking at hybridization. Types of bonds that are there, all those consequences, bond lengths, bond strengths. I think we're ready to move into physical properties handout, which is pink. Any questions though up to this point? Uh-huh.
Is there a difference in the interaction whenever you have a lone pair come up into a pure orbital? Is that interaction between that pure orbital and another pure orbital different than a normal, interaction? If you didn't have a lone pair in a pure orbital, you had a regular,
You're talking about the interaction between the lone pair and the p orbital?
yes, and the other, and the adjacent pure orbital. Is that a different interaction than when you have a normal pure orbital and a
No, it's not that much of a difference. The difference is, usually in a structure of the draw, we don't show that interaction. Look at Cipro. Does it show the pi interaction? No. You have to just know it's there. Because when this type of thing is going on, our regular drawing doesn't illustrate it. You have to know it's going on. It's called resonance. Now later on we'll learn how to draw resonance structures. And we'll actually draw discrete structures that do show it. And then we have to talk about other things like blends and resonance hybrids. Physical properties, I reckon let's introduce it. We'll see if we need to pick up anything in the previous handouts. Next time, again, 7:30 if you want to be here on Friday. I'll be here to answer any questions there. Okay, physical properties, including things like solubility, which we'll be doing in lab this week. This handout includes polarity, IMFs, boiling point, melting point, solubility, solvents, acid-base extraction. Handout today. Sorry I didn't get it earlier. White, it's one handout, just take one. That's your acid-base handout. Some warm-up questions there. And on the back side there. And we're ready to look at polarity. Something like H2, nonpolar. Non-polar covalent bond. Okay? 2 electron covalent bond, but the electrons there, 2 electrons, right? They're equally distributed between the 2 nuclei. Okay? So we call that nonpolar. On the other hand, something like HCl, chlorine much more electronegative. And so the electrons here don't sit exactly between. Instead, the electron density is more like that. The 2 electrons, which we call the electron density, actually sit closer to the chlorine nucleus. And so this unequal distribution of the electrons we call polarization. Now the net molecule is neutral. But we say that, just like in physics, if the electrons are sort of perturbed, it leaves a partial positive, and over here it's more partial negative. It's like physics. We can show that with partial plus and partial negative. These are not formal charges, these are just partial charges as a result of polarity. Or we can also show it with this dipole arrow, with the plus end being over here and this saying the electrons are being pulled that way. So HCl is a classical polar molecule. Okay? What are the consequences of that? Do you know? For example, if you put hydrogen in an electric field, it will not respond to anything. If you put HCl in an electric field, it will. The plus end will line up a certain way. Because that thing there, the HCl, has a plus and minus portion. And it will respond to an electric field in a certain way. All right? And that's a consequence of polarity. There are many consequences of polarity. All right? And you talk a little bit about stuff in physics. Okay, so we'll pick up here, hit the ground running here. Please be looking ahead. See some of you in lab. We're meeting downstairs. That's it. We haven't had a quiz yet, right?